Welcome to the next section of the Introduction to 6502 Assembly Programming. In this one we're going to be covering the logical operators. And I've realized I'm kind of rushing through these topics a bit, so hopefully I give enough detail. If not, feel free to leave some comments and I can go in some more detail. Yeah, this is a basic introduction to the ideas, at least. So let's look at the logical operators. All right. Logical operators are typically introduced in kind of the mathematics of computer science. And in that section, I think we just did add and subtract and, conversions between different bases. But if you take an intro to computer science class, they'll also include all these logical operators because these aren't typically covered in, your standard mathematics classes in elementary school, but they're used throughout programming, at least lower level programming, pretty extensively. All right, so the first operator is the AND operator, and we have here in the bottom left-hand corner what's called truth table. And the way you read this truth table is this is the value for A, this is the value for B, and this is the result of that operation if those two are the inputs. Now what the AND instruction says is that if both A and B are both true, or 1, then the result is 1. If both of them aren't 1, then the result is 0. So we'll see here in the truth table, if we have 0 and 0, the result is 0, obviously. And if we have A is 0, but B is 1, the result is still 0, because they both have to be 1. Similarly over here, A is 1, but B is 0. That's still a 0 because they're both not 1. And then down here, we have the only 1 because both A and B are both 1. So there's a 1 there. And that's the AND operation. This is operating on a single bit, but as we've said in the previous sections, 6502 is an 8-bit machine. So it's actually going to do 8 bits at a time. So let's look at an example of that. So the AND operation is often used for masking. That's one of the useful benefits or uses, and that's kind of the example here. So here I've kind of emulated what a game controller might report. It might have a byte that represents all the buttons that are currently pressed. So this register, this RAM location, has all the buttons that are being pressed right now. So we're pressing up and to the right and A and B at the same time. But let's see, we just want to check if we can enter that pipe, right? And so we just need to see if the up button is pressed. So what we can do is we can take this register and AND it with a 1 in the position that we want to check. And the result will have a 1 or a 0 in that same bit position if it's 1. So if up was 1, then the result would be 1. If up was 0, then the result would be 0. And that's because we're ANDing it. All the other bits, you see, we don't care about them. So even though some, they're pressing right, that's a 0 because we have a 0 here. So we're effectively masking off all of the other buttons and just looking it up. And you can kind of see here how this can be used with the 0 bit to check whether just up is pressed. Similarly, if we move a bit position, we want to see if we're pressing down. We can use a mask like this, and the result would be 0 because the down button is pressed, or not pressed. And all the others are 0. So here, we could do this and. We could say take this address, and it with this value, and then if the result is 0, by checking the status bit, then we know that down isn't pressed. So the result of the AND operation is going to modify the negative bit and the Z bit. Next logical operator that we're going to talk about is the OR. And just like its name says, it's going to be true if either A or B are true. The more formal name of this is inclusive OR. So let's look at our truth table down here. We have A and B just like we did before with 0 and 1s here. If A is 0 and B is 0, then the result is 0. Neither of them are 1. If A is 1 and B is 0, we get a 1 here now. Because remember, it's if either of them are true. And this is a 1, so that becomes a 1. Same thing with this position right here. A is 0, but since B is 1, if either of them are 1, then this becomes a 1. And then in the case where both A and B are 1, both of them are 1, but that's okay because either of them are still 1. And so that's the truth table for the inclusive OR. On the last slide, I forgot to mention, if you looked at it, I had an ampersand here, and that's like a C notation for a bitwise, and the pipe here is a bitwise OR. Different languages have different syntaxes, but that's fairly common syntax for a lot of languages that have bitwise operators. All right, so here we have an example of an OR operation. We have a register with this value here, 93 hexadecimal, if you remember from previous sections. And we're ORing it with this value here, 40 hexadecimal. And so what we're going to do is just test every bit to see if either of them are true. So 1 and 0, well, there's a 1, so that's a 1. 1 and 0, there's a 1, so it's a 1. 0 and 0, so it's 0. 0, 0, 0. 1, 0 becomes a 1. 0, 0, 0. 0, 1, 1. 1, 0, 1. So you can see anywhere there was a 1 in either of them, it gets set to the bottom. So it kind of combines them. Anything that's set will be set in the result. This instruction modifies the N and Z bits just like the AND instruction. The next one is a bit more wonky. I think AND and OR are pretty intuitive for most people. They kind of get what AND or OR mean, from the English words. The XOR is the exclusive OR. And what that is if A or B are true, but not both of them. So it has to be only one of them are true. This is often used for toggling a bit, but hopefully we'll see that in an example in just a second. Let's look at the truth table first. So here we have our A and our B, and again they have the possible values of 0 and 1. And so if we XOR these together, 0 and 0 will produce a 0 because neither of them are true. Remember, one of them has to be true, but not both. Here, A equals 1, but B equals 0. So one of them is true. One of them are true? I don't know. English is not my forte. One of them are true, but not both of them, so this is a 1. Next, we have a equals 0, b equals 1. Again, one of them is true, b is 1, but a is not, so that's equal to 1. And so far, this has matched the inclusive OR table. The difference here is this bit. When both a and b are true, then the result of an XOR is 0. Because remember, it says, but not both. All right. So let's look at this, a similar example to the previous one, and see how the XOR works. So here we have this value, and we're going to XOR, kind of the caret is the standard notation for a lot of languages for XOR. And we're going to XOR this value in. And so here we have a 1 and a 0, so this will become a 1 because one of them are set but not both. Same thing here, that's a 1. These are both zeros on those two columns, so everything's 0, it's a 0. In this column, they're both 1, but since both of them are 1, the output becomes a 0. In this one, all zeros. And these two, again, one bit is 1, the other is 0, so that output is 1. So that's how the XOR works. Like I mentioned, it's often used for toggling. If you wanted to flip a bit without knowing what the value is, the XOR toggles it. And we can see that in this example. Anywhere we put a 1 into the value that we XOR into a number, that bit is going to flip. So we only have 2 1s, both in these two positions, right? And the value we XOR it with, here it has a 1, so it flips it to a 0. And here it has a 0, so it flips it to a 1. So you can see it toggles wherever there's a 1. And then it keeps the value for everything else. Wherever there's a 0, it just keeps the value. It's also a parity, right? Okay, so the XOR instruction sets the negative and Z bits like the other logical operators. So let's look at some of these instructions at work. I know we covered the logical operators, but let's look at what this looks like on the 6502. So we have an AND instruction, and what the AND instruction does is AND the accumulator with memory and put the results back into the accumulator. So here we have an instruction that says AND 3 hexadecimal. So we're going to AND the address at address 3, or the value at address 3, with the accumulator, and put the results back into the accumulator. Right now the accumulator has F0 into it, and address 3 has 88 in it. So both the accumulator and the value at address 3 go into the ALU, and then it writes back the result into the accumulator, which would be an 80. The reason that it's an 80, let's look back, is that this is an F0. So that means the top 4 bits are all 1 and the bottom 4 bits are zeros. With an AND operation, both bits have to be set to 1. If we have 88, that means it is a 1 0 0 0 and a 1 0 0 0. And so if we think of this as nibbles, this F0 is effectively saying keep the top nibble, and this 0 at the bottom is mask off the bottom nibble. And so this 88, we keep the top 8 and we mask off the bottom 8. So that's how it turns to 80. If you didn't quite follow that, then what I would suggest that you do is go back to the introduction to computer science slides. If you don't remember the hexadecimal to binary conversion, or pull out your calculator and do these calculated conversions of these two values. Write one value, then the next value below it, both in binary, and then do the truth table results of each one of those, just like we did in the prior slides. And verify that result to kind of understand it. Maybe make up your own numbers, start ANDing stuff together and see what happens. But this is the way the AND instruction works. It takes the accumulator value, ANDs it with a RAM value, and puts the value back into the accumulator, the result into the accumulator. The second type of AND instruction that I have down below, you can also do this. Instead of using a RAM location, you can do a literal value and a literal value into the accumulator. So this second instruction here would AND this literal value with the accumulator and store the result back into the accumulator. All right. Hey, look. I actually created a slide for it. I was saying you should do it on your own, but I guess I did it for you. So let's look at the example from that previous slide bitwise. I forgot I had added this. So in the accumulator, we had F0. And F0 is represented as 1111, that's F, and 0 is 0000. Then in our RAM address, we had address 88. And the conversion to binary is 1000 1000 88. ANDing them together, remember that both bits have to be 1 for the result to be 1. So 0 0 0, here we get a 0 because this one is a 0, so the result is 0. Same thing for these three. All of those become zeros because this one is 0. And then this topmost bit, both of them are 1, so there's a 1 left. And then converting that back to decimal, we have an 8 and a 0. So we get 80 hexadecimal. So you can kind of see how the AND operation is used for masking. All the bits you want to keep, you put 1s in the position. All the bits that you want to mask or hide away, you put 0s. And then you AND it. And that's exactly what happened. You'll just wipe out all the values where you put 0s. All right. So I had slides for the second example too, the literal. So here we'll go through the literal example too. The AND, when you use the hash mark, just like the other instructions with the hash mark, uses the literal value instead of the RAM value. And so this is going to AND 0F into 55. So I challenge you, pause video right here, do this yourself, or use the calculator, see what you get, and then see if you get the results that match what I'm about to tell you. So what happens when we add those two together, or AND those two together? The result of that gets stored back into the accumulator, and it's 0, 5. Just like the last example where we had F0, and this one we have 0F. So it's masking off the top nibble here, and keeping the bottom nibble. And so we wipe out the top nibble, and we kept the bottom one. It doesn't have to be Fs. I used F as an easy example, but you could AND 0, 1, and then it would just test one bit of it. It could be 7F, and if you did 7F, it would just be masking off the uppermost bit. But that's the way the AND instruction works. Hopefully you got that same result. let's throw back to the last example, or the last episode, and show you an additional way the AND instruction works. So there's another way another addressing mode, the indirect mode that we talked about with the X and Y registers. So this one works too. So this is what can be a little confusing when you start to read code for the first time, right? We have 3 different AND instructions here. They each operate completely differently. But hopefully now you're starting to understand the difference. This first one is AND the accumulator with this specific address directly. Well, the value at that address. This AND is saying take this literal value, take this value right here, and AND it with the accumulator. This one is saying take the value at this address. This one is saying take the value at this address, offset by the value that's in X, and AND that with the accumulator. So here, if we have X equal to 1, and we execute this instruction, then what the accumulator, or what the ALU is going to do, is it's going to take the value at address 4, right? Because we have a base address of 3, plus our offset of 1, equals address 4. So the value at address 4 is going to go to the ALU and get ANDed with the accumulator. Then the result of that operation is going to get written back to the accumulator. I guess I don't have a slide showing the result here, but good opportunity for you to go off and try it yourself. But the point of this slide was just to show that, you can do a direct variable and a literal and an indirect and. So this is a direct and an indirect and. And there's even more modes I haven't covered yet, but I don't want to overwhelm you. But those are kind of the main ones that you'll see. Okay, so there are 2 more instructions here. The EOR and the ORA instructions, and those are the exclusive OR with accumulator or the inclusive OR with the accumulator. So let's look at the variations of those. So before we saw in the logical section, we saw inclusive OR and exclusive OR, and we said they were OR and XOR. In 6502 assembly, those instructions are called EOR and ORA. So those are going to perform the exclusive OR operation or the inclusive OR operation. And just like AND, all of the same addressing modes or modes of operation apply here. Direct, literal, indirect. So the same thing as AND, except you're going to apply the truth tables for an exclusive OR or an inclusive OR. All right. Here, I'm going to, instead of explaining everything else in the 6502, because it's a vast amount of information, I'm going to teach you how to fish. So instead of providing you with the fish as the proverb says, I'm going to teach you how to fish. And I'm going to show you this website that has all of the 6502 assembly instructions on them. And hopefully at this point, I've shown you enough instructions and talked about status registers and the accumulator and index registers that you have a fundamental basis enough to kind of look at this website and understand what it is. And this has all of the information about the entire instruction set on there. You just have to know how to read it. And I think at this point, you probably do. So let's jump over there. And I'll still have slides for all the rest of the things that I think are important and deserve a bit more description. But I want to show you this so you can go over there and look and kind of solidify some of this information. So let's take a look at that website. All right, so this website, you can copy the URL from there. Shows you syntax like we mentioned before. So we have, binary, hexadecimal, and decimal. Note they don't show octal because you should never use octal. Some assemblers don't support octal because you should never use octal. But some do, but you should still never use octal. And then here they also have, examples using literal values rather than address values. It has a brief description of the registers that we've talked about so far. And we've talked about all of them. The accumulator, the X, Y, program counter, stack, status. Next, they have a description of all the status bits. So you can, read what they are. We talked about some of them. We didn't talk about all of them. And we haven't talked about a lot of them in full detail. So some of this might not make as much sense. But yeah, you can read that there. Talks about the memory layout. We talked about that in the last section. The 0 page, the stack, and the general purpose addresses. So that's all good. It talks about address modes here. And I am not going to cover this immediately, but we've talked about some of these. So we've talked about the immediate using the literal value here, putting that in front. The absolute, which is, accessing an absolute address. We've talked about using the indirect address with X here, an indirect address with Y. We've talked about those. And then there's some that we haven't talked about that are more advanced, like the absolute indirect, 0 page. I'm not going to cover these. You don't see them as much, but I'll be happy to create sections on those addressing modes if people want to see them. But you don't generally see the rest of those modes of operation. Then let's jump down here into the instruction set description. So let's look at LDA. This is, I think, the first instruction that we talked about. I talked about these three because we talked about the accumulator first. So we did LDA and STA first. So LDA, remember it went and took a memory location and loaded it into the accumulator. And so that's what this notation is saying right here. Take a piece of memory, load it into the accumulator, the arrow. And the status flags that are set are the N and the Z bit. So these are the status flags that are set. And then here is the supported addressing modes. And so we talked about absolute, and you can click back on these if you don't remember what each of these are. So this one would be, you can LDA $0003, and that will load the absolute address of 3 into the accumulator. The immediate is right here. And so this is if you want to load the value of 5A into the accumulator, you do LDA #5A. And similarly, we talked about the X and the Y, the indirect addressing modes. And you would put, for those, the value of the base address, comma, X, comma, Y. And so you can see the instruction, what it does, the statuses that affect it, and the different ways that you can use it. The other thing it shows here that I'm not showing on the slides is it shows the opcode. And remember back to that slide where we talked about computer architecture, we talked about opcodes and operands. And so these tables have all the values for all the opcodes that go into it. And then if you go into these addressing modes, it'll give you a description of how the operands for each of those modes work. And then it has these for every single instruction. So let's pull out another one that we've looked at. Here, increment. We talked about increment briefly. Increment a memory location by 1. So you have a memory location plus 1 gets stored back into the same location. Right? So you just add 1 to the thing and store it back to where it was. And that works in absolute addressing mode and indirect addressing mode. You can see here that the immediate or the literal mode doesn't work, right? Because a literal doesn't have an address. So where would you store the result to? There's no reason to add a value to a literal, because if you wanted to use a higher number, you just write a different literal. So there's no reason to support a increment a literal. You're going to increment a variable, but you don't increment a literal. Similarly, so we have the increment x instruction, the increment y instruction, the decrement x and decrement y, where we said it's the x register plus 1 goes back into x. And here, only this implied mode is the only mode that's supported, because in x, increment x can only increment the x. That's all the instruction does. So it's implied that x is going to be the one that is incremented. Same thing for y in here. So that's how you read these tables. And yeah, down here, logical section that we just covered, we have the and so it's the accumulator and your memory stored back into the accumulator. And again, that works with the memory location being an absolute address or the memory value being a literal value. So the way you would read this is the accumulator ANDed with a literal value for the memory stored back into the accumulator. So I would encourage you to look over that website, run through these slides, maybe go back through the slides, and as I'm talking through an instruction, pause it and look over at this instruction set and become familiar with how to read this table. Because once you can start reading these tables, you'll understand how to do everything. I mean, this is the complete description of all of the instruction set in this device. And my slides are just describing these in more detail, but once you unlock the understanding of reading this page, yeah, you don't need my slides anymore. All right, so let's go back to my slides now that I've made them useless, and let's talk about what's next. Next section is going to cover shifts and rotates. Again, kind of similar to the logical operations that we just did, but a bit different, and I felt it warranted its own section. If you have any questions, feel free to leave them in the comments below or reach out to me in Discord. I'll be happy to answer them. Thank you.